yeah, oops, yes, plus O2 gas goes from H2O gas. I'll put a 2 here.
Yeah.
Okay, so what are these numbers? 2 in front of the H2, 1 in front of the O2, and 2 in front of the H2O. What are those called?
Coefficients.
Coefficients. Very good. Coefficients. I just usually abbreviate it like COF. Sometimes they're called, and I kind of stumbled on this the other day, but sometimes they are called stoichiometric coefficients. Yep. And so not only do they give you the same number of oxygens and hydrogens on either side of the reaction arrow by making it 2, 1, and 2 stoichiometric coefficients, but it also is kind of like a recipe. So it says that like 2 molecules of H2 will react with 1 molecule of O2 to form 2 molecules of H2O. So like it's a recipe. We said that's quantitative information. Well, the stoichiometry of a reaction is given by a chemical equation, and the stoichiometry is embedded in those coefficients, in the stoichiometric coefficients. So all stoichiometry is amount, the amount. And the best way to talk about amounts is to talk about either like molecules and formula units and atoms, or we're going to scale that up to relative numbers of moles. Okay, so that's the rest. Stoichiometry is the amounts that of the reactants that forms amounts of products, and if you have balanced your equation, then a stoichiometric coefficient says stoichiometry. So you guys did this in the lab the other day where you basically oxidized magnesium to form magnesium oxide, and that is the balanced equation. Now, to me, when I come up with those stoichiometric coefficients, when I come up with those coefficients of 2, 1, and 2, I usually think on a small scale, because I usually think I'm balancing magnesium and oxygens on either side of the reaction arrow. So I usually think of this as being 2 magnesium atoms reacting with 1 molecule of O2 to form 2 formula units of magnesium oxide. Well, we could scale that up. And instead of those coefficients of 2, 1, and 2 talking about the small scale, we can talk about the big scale. The big scale now would be bundles of particles, specifically moles of particles. So instead of saying 2 atoms, magnesium atoms, we could say 2 moles of magnesium atoms react with 1 mole of O2 molecules to form 2 moles of magnesium oxide. And the other day, we kind of ended with balancing equations by being able to use fractions as stoichiometric coefficients. You can have a half a mole. You can have 0.5 moles of magnesium atoms. Okay, you can't have a half of an atom, but you can have a half of a mole. Very good. Well, those stoichiometric coefficients that you guys did to use to balance your equations. Again, what do? They tell the overall stoichiometry of the equation. They tell relative amounts. So it's funny because the title of this was Simple Stoichiometry. Okay, so all a stoichiometry problem is basically not necessarily moles, relative moles of reactants and products, but it goes to probably more like grams of reactants, grams of products, grams within products and products, or grams within products and products, reactants and reactants, that sort of thing. What I started to say, I think it's funny because it says simple. That suggests that there's something called not simple stoichiometric calculations, and we'll get to that on Friday. But ordinary, simple stoichiometric problems, that's what we're going to talk about now. So in order to perform this sort of calculation where you're going to go between amounts of either reactant or product, you need to have the balanced equation. So on your test, your Unit 2 exam, will be here before we know it, and your Unit 2 exam, one of the things you'll have to do is balance equations, just like you did for your homework. And then you'll also have to do a stoichiometric calculation, but I won't have you do both. I won't have you balance it, and then from you balancing it, go ahead and take it and do the stoichiometric calculation. So we've been talking about taking equivalency statements and making them into conversion factors. So as we do that, take an equivalency statement, make it into conversion factor, that's a ratio. That's a ratio. We can either do it like this, or we can flip it depending upon what units need to cancel. So from any balanced equation, we can come up with stoichiometric ratios. And all they are is saying relative moles of something to something. They can kind of be thought of as coming from equivalency statements into ratios. Stoichiometric ratios are used to work stoichiometric calculations. And like this says, what is your OpenStax? OpenStax uses stoichiometric factor. So we're going to pick on this pick on this reaction that's represented by this balanced equation. And we could, for instance, if we were focusing on the relationship between magnesium and oxygen, what we would do is go find magnesium, go find oxygen, and look at their stoichiometric coefficients. So we can say that there are 2 moles of magnesium for every 1 mole of oxygen, 1 mole of O2. Or we can say there's 1 mole of O2 to 2 moles of magnesium. Starts with the letter R. What's the relationship between this pair of ratios? They are it's not flip, it's called, they are the reciprocal of each other. Yep. So we can use these ratios to go back and forth depending upon what we have. We'll put the units in the bottom. Like if we wanted to go from moles of oxygen, if we wanted to go from moles of O2 to moles of magnesium, we would use this one. If we wanted to go from moles of magnesium to moles of O2, we would use this one. See how that works? Well, if we wanted to pick on now, so magnesium and oxygen, are they reactants or products? How many people think they're reactants? How many people think they're products? They are reactants. They are reactants. So we have reactants over here going to form products. Yeah, R to B. So we could, in that case, we were picking on 2 reactants. Well, what if we wanted to, instead of pick on 1 reactant and the product? We could do that. A lot of times I tell students I would just write down the units and then I go back up and look at what the stoichiometric coefficient is. So what does 2 moles of magnesium to 2 moles of magnesium oxide reduce to? It just reduces to 1 to 1. Sometimes students will say, well, Mrs. Snipes, why didn't I just go ahead and write this way? And it goes something like this. I like this because it gives more information. You know, it gives the stoichiometric coefficients. Well, the reciprocal can also be said or used if we need to. The last thing we didn't look at was what? O2 and MgO. Well, we could do that too, depending upon if that was our stoichiometric coefficient or stoichiometric problem. Any questions about that? So these big numbers, of course, come from the coefficients. Cool. Well, let's work a problem. And we're actually going to start out with what I call kind of a baby problem. And then we're going to kind of build up. This isn't normally the type of problem you would have. We're going to work 2 problems. The first one is how many moles, and a lot of times I will write underneath the equation what I'm after and this sort of thing. So how many moles of O2? So I'm going to go question mark moles is needed to react with 0.245 moles of Mg. So I'll find Mg and I'll put 0.245 moles. Sorry. So that's 245. So I like doing it this way because then it kind of hits you over the head. And can you see where all we need to do is use the ratio that gets us from, we're going to put moles of magnesium in the bottom, we're going to put moles of oxygen in the top, O2 moles, and then we just need to put the stoichiometric coefficients that are with those. So that's problem number 1. Problem number 2 looks like this, and problem number 2 isn't written very well. You would think it's a number of years since I used this slide, I would kind of clean it up. But it says how many moles of magnesium oxide formula units can be formed. So magnesium oxide, I'll put question mark moles. And that is our second problem right there. And that's based upon 0.245 moles of magnesium and sufficient O2. So working the second problem, if we want moles of magnesium oxide to cancel, what units will go in the bottom, the next term?
Magnesium, moles of oxygen.
Moles of magnesium oxide, yep. So let's work these. Again, these are kind of the baby ones. So we can go from moles of magnesium for the first problem to moles of oxygen using this particular, of the 6, this ratio. Yep, and we're going to put moles of magnesium in the bottom, and we're going to take this 2 from this 2. Moles of O2 in the top, because that's what we're going to, and that 1 comes from right there. So the second problem looks like this, where we're starting again with moles of magnesium, so we're going to put units of moles of magnesium in the bottom. This 2 comes from here. Look like one of these football play things. Moles of magnesium oxide in the top, because that's what we're going to, and this 2 comes from right there. All right. So then it looks like this. The first problem, the first term is going to be that 0.245 moles of magnesium over 1. Then this is called a stoichiometric ratio. A stoichiometric ratio coming from the stoichiometric coefficients. We want moles of magnesium to cancel, we'll put it in the bottom. We want to be left with moles of oxygen, in this case, we'll put it in the top. So a half of 0.245. Now notice there's no uncertainty brought by these coefficients, okay, but there is uncertainty brought here. So we need to round to 3 sig figs. And I get, round to 3 sig figs, 0.123 moles of O2. The next one looks similar. We're going to use as a starting point 245 moles of magnesium. I usually put that over 1. And this is literally where I tell students I would literally write moles of magnesium. I write the units first. And we're going to what moles of MgO. I would write those units. And then I would go up to the balanced equation and pull down the coefficients. So if you can read through my red, that's 2 moles of MgO over 2 moles of Mg. And we're left with units of MgO, so dang, it's the same, right? Yep, it's the same number anyway, but the units now have changed. So 0.245 moles of MgO. There's a song out there, was it Farmer Had a Dog and Bingo, what's his name of? A B-I-N-G-O. I always think of MGO, it's B-I-N-G-O. Anyway. All right, so that is actually, here in a minute when we do a regular calculation, it's not going to be from moles to moles. It's actually going to be from grams to grams. Okay, so this is what I call the heart of stoichiometric calculation, and usually it's not like this. Sorry, it's not. So usually you're going to run into a problem more like this. We're going to still pick on this reaction with this balanced equation. So let's go ahead and write under the equation what we're after. So it says what mass of oxygen is needed. So under oxygen, I'll put question mark grams, is needed to react with 0.30 grams of magnesium. Yeah, I have a slide coming up here in a minute, and you cannot go directly from grams of something to grams of something else using these stoichiometric coefficients, because these are relative moles, not relative grams. So instead, what you're going to see us do is we're going to go from grams of magnesium to moles of magnesium. How can we do that? What's molar mass. And then we're going to go from moles of magnesium over to moles of O2 using stoichiometric ratio. And then we're going to go from moles of O2 to grams of O2 using the molar mass. So that's kind of what we have going on here. A minute ago when I called it the baby problem, you basically did this part down here, the moles of magnesium to the moles of O2. So we're adding kind of a front step and a tail step. All right, here we go. So this is where I said, you know, those ratios, we've been talking about the stoichiometric ratios that come from the stoichiometric coefficient of the balance equation. We can use those quite handily to go from moles to moles, but we can't use them to go from grams to grams. Does not work. That's okay. So kind of what I said looks like this. And these stoichiometric calculations have quite the pattern to them. So you're going to take the mass that you know about, the mass of the thing you know about, in this case it's a reactant, to go to moles of the reactant using molar mass. And then you're going to go from the moles of what you know the mass about to the moles of the thing you're trying to get the mass about using stoichiometric ratio. And then you're going to go from now the moles of what you want to know about to the mass of what you want to know about using its molar mass. Now, it's possible you basically have kind of three calculations there. Now, sometimes students I've seen quite successfully break it up into three parts, you know, to kind of label them apart. But what you're going to see me do is basically take these three parts and make sure I label everything carefully and make one little calculation out of it. So here we go, stoichiometric calculation. So you can see we're going to need the molar mass in two places. Need the molar mass of magnesium, need the molar mass of O2. So this slide knocks out the molar mass for everything. Of course, the molar mass for magnesium, I just have to pick it off the periodic table, 24.31 grams per mole. For the molecule O2, I have to take 2 times 16.00, that gives me 32.00 grams per mole. And we don't need it for this one, but I'm going to go ahead and we'll need it for this follow-up problem. What we're going to do, the molar mass for magnesium oxide would be 1 times 24.01, sorry, 1 times 24.31, which is magnesium, plus 1 times 16.00. So the molar mass of MgO is 40.31 grams per mole. So that's kind of like our background calculation. All right, so let's work it. And like I said, you're going to see me kind of string them up. The first term is going to be the mass of magnesium, that 0.30 grams of magnesium over 1. I'm going to use the molar mass of magnesium from the previous slide. Since I want grams to cancel, I'm going to use what? The flipped version, I call it, the molar mass. So 1 mole of magnesium over 24.31 grams of magnesium. One of the things I've seen students kind of falter on, it's important. Sometimes you have to be explicit and sometimes it's optional. It is not optional to be explicit. You have to say grams of what, moles of what, grams of what. All right. So now units of grams of magnesium cancel. We have units of moles of magnesium. Now I can use that stoichiometric ratio. So I want moles of magnesium to cancel, and I want to put moles of O2 in the top, and then I just go up to the balanced equation and grab their coefficients. So the stoichiometric ratio looks like this. 1 mole of O2, and the 1 came from the 1 in front of the O2, over 2 moles of magnesium, and 2 came from the coefficient of magnesium. At that point, moles of magnesium cancel, and we're left with units of moles of O2, and we're almost done. So the last step is to kind of, say unpack, but well, to go from moles of O2 to grams of O2 using its molar mass, that 32.00 grams per mole. In this case, since we want moles to cancel, we're going to use the unflipped version of the molar mass, so 32.00 grams of O2 per 1 mole of O2. And in chemistry or in physical science, physics, biology too, but as long as you set up problems so that you're honest about your units, then your units should tell you if you have it set up right. And our goal was to go from grams of magnesium to grams of O2, and we definitely had grams of O2 units here. So sig figs, what do you guys think? Finger use. 2, up, 2. Yes. Yep, just 2. 0.20 grams of O2. Any questions about that? The follow-up question is going to be, so I'm going to put 0.30 here, grams, and I'm going to put 0.20 grams here. The follow-up question actually is going to be, if you have 0.30 grams of magnesium and sufficient amount of O2, what mass of magnesium oxide will be formed? What do you think the mass would be formed? Conservation of matter, conservation of mass?
0.5.
0.5. 0.50. Yep. Now, I've never, on a test, asked you to do this, but because you can really just knock it out. It's a good check, though. Let's go ahead and do it the long way, if that's okay. So, like I said, we're starting, this is the follow-up question, and we have 0.30 grams of magnesium. It says with sufficient, and we'll talk, all sufficient means is we have, I'll just put lots. We have lots of O2. That means we have more than enough to react with our magnesium. And then the question mark is, or the question is, what mass of magnesium oxide will be formed? So again, we're going to go from grams of magnesium to moles of magnesium. How are we going to do that?
Molar mass.
Molar mass, yep. And then we're going to go from moles of magnesium to moles of magnesium oxide. How are we going to do that? Yep. Stoichiometric ratio. Very good. And then we're going to go from moles of magnesium to grams of magnesium. How are we going to do that? Another molar mass. Yep. That's it. And we're going to get 0.50. So our starting term is going to be that 0.30 grams of magnesium. So we want grams of magnesium to cancel, so we're going to use the flipped version of the molar mass. So that's 1 mole of magnesium over 24.31 grams of magnesium. Now we're to the heart of the stoichiometric calculation. We want to skip from moles of magnesium to moles of magnesium oxide. So what does that ratio look like? We want to go from moles of magnesium to moles of magnesium oxide.
Magnesium's on the bottom.
Yep, magnesium's on the bottom. And we'll drag a 2 along with that. So 2 moles of magnesium at the bottom, 2 moles of magnesium oxide at the top. Yep. Yep, yep. 2 moles of magnesium oxide over 2 moles of magnesium. Perfect. And then you guys told me I can go from moles of magnesium oxide to grams using its molar mass, which if you look back a few slides, we had it as 40.31. So we use the non-flipped version of the molar mass to go from moles to grams. That last term, 40.31 grams of magnesium oxide over 1 mole of magnesium oxide. So working problems, take your time, let it simmer, but make sure that you label everything. And I use the word species to just indicate anything. So species could be a reactant or product, so you need to label everything. So how are we going to round this one? 2. Voila! What do you think if you were in the chem lab doing this experiment? Do you think if you reacted 0.30, well, you guys did this. If you react which you didn't do in this context, 0.30 grams of magnesium, would you necessarily get 0.50 grams of magnesium oxide? You might. No, you guys, no. I'm just kidding. No. No, anybody in the lab. I'm just kidding. I was trying to make fun of your lab. You guys do a great lab. So yeah, this is what we call, I'll go ahead and use the word for it because we're going to use it later. This is what we call a theoretical yield. It's what you think you should get back. And then, yeah, I kind of was kidding you guys about If you think you really would get 0.50 grams of product, and probably not, because it's usually inherent, the cards are stacked against you. It's usually inherent in experimental design, but you can't get it all. All right. So yeah, this was kind of the thing I asked you before about if you automatically knew that 0.30 grams of magnesium would pick up 0.20 grams of oxygen, what do you think the product would be? You said 0.50. And that's like a mass balance check. So there's definitely some problems in chemistry where you can check your answer. One of them is in coming up with an average atomic weight, the decimal number in a box. I'll use the periodic table to check your answer. Okay, so let's do another one. Hopefully we're good with it being balanced. Somebody already did the hard work for you. If I draw a brick wall, you're going to see that we have the same number of phosphoruses and chlorines on either side of the reaction arrow. I'm looking like 4 and 12, 4 and 12, and 4 and 12. Cool. We saw those videos recently. So here's the question that we're going to do. Remember, you can only work a stoichiometric calculation if you have a balanced equation. Okay? So we do have a balanced equation. So what mass of P4 is needed to react with 1.25 grams of Cl2? So again, I really like, and there are other times working chemistry problems where it helps to take this information, and if you already have the balanced equation there, why not put it underneath there? So what mass of P4, so I'm going to find P4 and I'm going to put question mark grams. What mass of P4 is needed to react with 1.25 grams of Cl2? So I'll put 1.25 grams of Cl2. So again, we're going to go from grams of Cl2 to moles of Cl2 using what? Yep, thanks, molar mass. Then we're going to go from moles of Cl2 to moles of P4 using what? Stoich ratio. And then we're going to go from moles of P4 to grams of P4 using what? It's molar mass. Yep, very good. So kind of like I did before, this is the molar mass. Do you guys have these in your notes, or can you jot them down? I'm going to write out the molar mass of everything. So the molar mass of P4 is 4 times the decimal number for phosphorus, which is 30.97. So it's a whopping 123.88 grams per mole. And then to work this problem, we're going to Cl2, so we need its molar mass. 2 times 35.45 is equal to 70.90 grams per mole. And not in this problem, we're going to do a follow-up problem where we're going to go to moles of product, PCl3. So we need its molar mass. So we take 1 times the decimal number for phosphorus, which is 30.97, plus 3 times the decimal number for chlorine, which is 35.45. So it's the heaviest of everything. So its molar mass is 137.32 grams per mole. So a lot of times when you're working problems, this is what I'm going to see you work first. So how do I say this? Because there's a pitfall that I see a lot of times students go into, and you guys have had chemistry, so you probably haven't. You've gotten over this problem. But for some reason, a lot of times I will see students try to take this number and put it in the molar mass somehow. And no, you don't. This molar mass is independent of the fact that we have 6 moles of Cl2, okay? Do not take that number, nor do we take this number, okay? Molar masses are what they are. Okay, good. So let's do it. So the first term is going to be that mass of Cl2, which is 1.25 grams of Cl2 over 1. And then you guys told me I can get to moles of Cl2 using its molar mass. So if you flip back to the previous slide, what does that ratio look like? What are the units in the numerator of the next ratio?
Moles.
Moles of
Cl2.
Yeah, moles of Cl2. And what are the units of the denominator?
Mass.
Grams of CL2. Yep. Very good. So this is a clean, just a clean molar mass, CL2. So grams of CL2 cancel with moles of CL2. So what units go in the denominator of the next term? Moles of CL2, very good. What number goes with moles of CL2?
6.
6, perfect. What units go in the numerator of the next term? Moles of P4, and then what number goes with that? 1. Very good. So 1 mole of P4 over 6 moles of CL2. So it's kind of, I call that the heart of stoichiometric calculation. Cool. So now we're ready to wrap it up. We go from moles of P4 to grams of P4. And how do we do that? Trick question. Molar mass. Yep. So we flip back to what we came up with the molar mass for P4. So we use the unflipped version of the molar mass of P4, which was 123.88 grams of P4 over 1 mole of P4. I'm liking it. So again, it's all about the units. It's all about the base. It's all about the units. So we have units of P grams. We have units of grams of P4. So how many sig figs? Yep. 3. I'm liking it. So 0.364 grams of P4 will combine with your 1.25 grams of CL2. Yay! Follow-up question is going to be, and again, you could get the mass of the product simply by adding these two together, couldn't you? But we're not going to do that. Okay, so we have 0.34 was 0.364, excuse me, grams of P4 reacted 1.25 grams of CO2. So what is it? I can't do it in my head. Yeah, 1.61. Okay, 1.61. All right, but let's do it. So yep, it says what mass of PCl3, so I'll put question mark grams of PCl3 can be formed from the reaction of 1.25 grams, sound familiar, of Cl2. And remember, I put the word lots over, I can't remember the oxygen before. And in this case, I'm going to put just lots over P4. Lots as in a lot. Okay. So let's see if we get 1.61 grams of product formed. So a few slides ago, we knocked out the molar mass of Cl2 and PCl3, and we'll be using those. So what's the first term going to be? Yep, 1.25 grams of Cl2. Very good, over 1. And actually, it feels like it's going to feel like deja vu, because it is like deja vu. Because when we went from grams of Cl2 to grams of P4, we had to use the molar mass next. So here we go. Molar mass of Cl2 is 1 mole of Cl2 over 70.90 grams of Cl2. So our units of grams of Cl2 have canceled. We have units of moles of Cl2. Now we're ready for the stoichiometric ratio. What units go in the denominator of the next term? Moles of Cl2, very good. What number goes in front of that? 6 moles. Good with that? Very good. What units goes in the numerator of the next term? Yep, moles of PCl3, very good. Moles of PCl3. And then what number goes with that? 4. Yep. That's it. So our ratio this time is going to be 4 moles of PCl3 over 6 moles of Cl2. So this 6 came from here, and this 4 came from here. Cool. So now we have moles of PCl3. We're going to grams. How do we get there?
Molar mass.
Using the molar mass. Perfect. So a few slides ago, we knocked that out and we came up with 137.32 grams of PCl3 per 1 mole of PCl3. So moles of PCl3 cancel. We're left with grams of PCl3, which is where we want to be. So how are we going to round it? 3. Very good. And we did get the sum of the two reactant masses. So 1.61 grams of PCl3. Goodness. Smiles all around. All right. So I changed things up a little bit, and I'll tell you why. But I want to take a look at this slide before we look at the next problem, the last problem. This is a busy slide. Of course, the rainbow around it means that it came from OpenStax. But if you look at it, there's only one thing we haven't done. We've done a lot of this. Well, how do I say? Not a lot of this, but do you remember when we talked about how you go back and forth between moles and particles? We said use Avogadro's number. And here's moles and particles, Avogadro's number. What we've been doing most recently is in a balanced chemical equation, we can use the stoichiometric ratio, here it calls a stoichiometric factor. We can use the stoichiometric ratio from the coefficient from the balanced equation to go back and forth between moles, right? And one thing we've also been doing is we've been doing a lot of this, haven't we? To go to moles, we can use the molar mass of the thing. Sorry, to go from mass to moles, we can use molar mass. Mass to moles or moles to mass, we can use molar mass. All right, it's a busy slide. Now, one more thing though. Have you guys ever used density to go from volume to mass? Yes, you have. Yeah. So you guys have actually already done that one too. It's a conversion factor. The one thing we haven't done, and we'll get to it here in a little bit, is we're going to talk about solution concentration. So if you have a solution, one way to say how much solute or stuff you have dissolved into it is to talk about its molarity. Some symbol for molarity is a big M. And if you know the molarity of a solution, you can actually go from volume to moles or from moles to volume. So we'll finish that up here. I know it's real busy, but you guys have done all that stuff. All right. So what I'd like to do, I think, how do I do this? Yes, come on. It's your turn. I'll put you on the spot. I haven't quite decided how I want to do this. I want you guys to work these problems before you go. You've got 10 minutes. So what are these problems? Well, they kind of come in two flavors. I'll go ahead and kind of I'll superimpose on this balanced equation what these problems are. Stoichiometric calculations are bad and good, / you have all sorts of different options. Notice in this case, they are giving us the mass of a product, O2, so I'm going to put 0.143 grams under my O2. And you can work together if you want to. The first question 1, is what mass of each reactant must have reacted to form that amount of product? So I'm going to put this as 1A, and this is going to be 1B. I'm going to put question mark grams. And then for the second one, is what mass of each of the other products must have been produced along with that oxygen. So I'm going to put I'm going to put 2A here, question mark grams, and I'm going to put 2B here, question mark grams. Now on the next slide, don't you guys have the molar masses of everything? Okay. So hey, I did that heavy lifting for you. It's not too bad. So. So work together if you want to, and I know your partner's not here, but You can work with Tristan if you want. Yes, in fact, would you mind? Put you on the spot. So you can, Tristan, why don't you go over there so you spread out a little bit.
Yeah.
So if you guys work together, and your ticket out of here is y'all can't leave until you have no problems. So it's fun. Everybody need a water cap? You should tell us. It's not going to put you to work, it's right.